So what we're going to do now is after we fit the model last lesson, we are going to explain the mathematics that the software is doing in the background after the model is fitted to obtain the forecast. Okay, forecasting is our goal when we do time series analysis. So the idea then, well, sometimes I shouldn't say that, sometimes we want to explain also when we use other variables particularly. But when we have just one variable and we want to forecast that variable, then the goal is just mostly to forecast, right? So we are going to see that the mathematics starts by representing the ARIMA modeling in a polynomial form. So this is pretty different from any other regression you have done. The polynomial form translates everything we do to the data plus the fitted model in compact form. So it's going to put everything in a very compact form. This is what I meant by holistic. ARIMA is a very holistic way of modeling everything, the trend, the seasonal, the stationary part, the random term. The math then is going to continue after that by expanding the polynomial and then writing the resulting complex model as something that is familiar to us, like a regression model. And with this familiar regression model, then we are going to forecast ahead as many steps as we tell the program to do, using the past values of the time series, using memory. Okay, so time series is about using memory, the memory of the past, to make decisions about the future, right? To predict the decision being forecast in the future. So, and then we are going to undo the pre-transformation, because what we want to forecast is the original time series. Nobody wants to see the forecast of a log of a time series. So you always have to convert your final forecast into what the original series is. If you took log, then you have to exponentiate. If you took a square root, you have to square. You took quartic root, you have to raise to the fourth power, and so on, depending on the transformation that you did. After the forecast, then we'll convert, as I said, the pre-transform. So that's very important not to forget it, not to get weird pictures. Okay, so why do you need that? Well, because by seeing your forecasting model as a familiar regression model, it will be easier for you to understand what ARIMA is doing. Of course, the process is not going to be anything that you're familiar with, but the final result is something that you'll be familiar with. So we should be able to also explain how forecasting works and how the multiplicative nature of ARIMA, which is what it is, multiplicative, helps us do good forecast. Okay, so let's start by remembering what we did in the last lesson. We identified a tentative model for the rooms data set, and the model was for the seasonally different quartic root of the rooms time series. So we pre-transformed, and then we took seasonal differences. We wrote this model in ARIMA notation form, and then we used the R code to translate this language into code executable that will give us the estimated model. And this is the estimated model, right? So what do we do with this now? Well, of course, we told the program to forecast, to predict using the predict function, and it gave us very beautiful forecast, right? So, but the things we want to do now are different. The things we want to do now are more the mathematics behind what the program is doing, right? So we fitted the model and we forecasted only after we made sure that the residuals were white noise. These are not the most white noise residuals that you can think of. And in fact, I'm going to ask you to improve this model later on. But okay, we stop there just to continue, to be able to continue with the process. And along the way, something is going to tell us that we should improve it. So the residuals, we are going to accept that they're closed. We are going to interpret this significant one here as one of the 5%, right? We said that. And now we retrace our steps. We took quartic root, we seasonal difference, we identified and fitted. And then we ended up the lesson 2 with this expression that you might wonder, what is that, right? Well, that expression is just the translation of what the estimated model is. Okay, so if you go back and remember, in this, we got these coefficients. We got the coefficient for the regular part, AR1 and AR2 for the autoregressive model that we identified for the AR part, which is these two here. And the MA model that we identify for the regular part. Remember, this first parenthesis is for the autocorrelations around the zero, right? Very few autocorrelations around zero. And the seasonal, everything that has an S in front of it, refers to the model that we came up with for the seasonal component, for the part of the autocorrelations that are around the seasonal components. And we apply the same rules, remember? So what we did is just take these and then put them in polynomial form. So this is another way to express the same model, a model that is ARIMA 201011 and is for a monthly time series. It can be expressed, the results of the estimation in this polynomial, and this one is going to be the trend, all right, the differencing, and this is going to be the MA part for the regular autocorrelations, the MA part for the seasonal autocorrelation. So that's what we're going to discuss today. What do we do with that? Okay, so what is each of these parts? So let's have the model again. The model is here, the estimation, and we put it in polynomial form. So we don't forget that we took the quartic root. Then this part here, 1 minus B12 y star t, represents that we seasonally difference the time series. And notice there is no coefficient when you are differencing, okay? There is no, we only have the powers of the backshift polynomial. And then, oops, I'm going too fast. And then the whole thing here, right? It means that we fitted an AR model of order 2 to the regular part, right, of the seasonally different quartic root. So everything that we did is summarized here. And it also has the coefficients. If you notice, we have 0.1082, 0.8148 is here, and so on, right? So the idea is, why is it negative? In a moment, you'll see why, okay? So it has to be negative because the coefficient is positive. So in reality, okay, in reality, what we have is that YT, okay, let me write it here for you. YT is equal 0.1082, YT minus 1, plus 0.8148, YT minus 2, right? That's for the AR part. And it's not just Y, it's the difference Y, okay? Remember that that's for the difference ones, okay? Right? So the idea is, so that's for this thing, that's for the difference part. So what happens is if you go here, if you bring it to the left hand side, right? So this is CT, and this is the W. Suppose this is the AR part, okay? So this is just the AR part. So the AR part of the model for the regular part is CT minus 0.1082, CT minus 1, minus 0.8148, CT minus 2, equal WT, right? So then you can see that this is 1 minus 0.1082 B minus 0.8148 B squared, C sub T equal WT. But C sub T is 1 minus B to the 12 Y star, okay? And so that's what this is doing. We are translating the AR part for the regular. And remember, this is for this is for the lower lags, okay? For this part of the ACF. Now, in the right-hand side, everything that is MA goes to the A. So this part here is all AR, okay? The MA part goes all on the right-hand side. So we have two models, right? We have the model that we identified for the regular part. Remember, we have this. Remember, the model we had was ARIMA 201, right? And then we had 011. So for the MA part of the regular, is gonna be this one. MA model part of the regular was just an MA1, and this is the coefficient, right? So this is like saying that the Z sub t at the regular part was also, the MA part, was equal to WT plus 0.5825 WT minus 1, which is equal to 1 plus 0.5825 B, if you use the backshift polynomial, W sub t. And then we did the same for the seasonal part. For the seasonal part, we identified also an MA model of order 1, right? So this was for the seasonal. For the seasonal, we had WT plus minus, actually, if we estimated, the model is negative, this is negative, minus 0.5177 WT minus 1. So this is 1 plus 0.5 B WT. So notice how we are using the backshift polynomial, which is why we learned it earlier, because we use it a lot in ARIMA. Okay, so we write the model like that. And what's the point of writing it like that? Why would we waste our time? Well, this is very helpful to see what is the final forecasting model. And this is how this works really. First, we check the polynomials for stationarity and invertibility. The polynomials, these are the polynomials. Polynomials in the backshift operator. So notice the backshift is going to act like a variable, and we are going to check these polynomials, but we're going to leave that for a separate lesson, the third lesson today. Then if there is a stationarity and invertibility, which are necessary conditions for us to be able to forecast, then we are going to expand the polynomials in B. So what does that mean? It means I'm going to multiply the polynomials. So this is the model fitted to the trended to the difference, seasonal difference as quartic root. Well, I just multiply these polynomials. Okay, so this is the polynomial on the left times the polynomial 1 minus B12. And that gives me all these other polynomial in powers of the backshift operator. I do the same with the right-hand side. I multiply the polynomials. And I obtain another polynomial. And notice how it brings us to powers of 13 and 14. So the memory is pretty large when you have seasonality, right? I mean, a whole year has to be, because the seasonal today remembers the seasonal from last year, right? So this is like the time series today remembers what happens a year ago because of the seasonality, because of this repetitive movement that we capture with our differencing, right? So, okay, so that we got our polynomial written, then we start to undo the back shifts by putting what they mean in terms of y, right? So that means that we bring the yt here. So 1 times yt is yt, minus b12 times yt is yt minus 12. So that means you need to remember. If you don't remember, please go and review the lesson where we studied the backshift operator. What does it mean? B to the 12th yt. It means yt minus 12. Then minus 0.108 to the b is minus 0.1082 yt minus 1, because the power of the operator is just 1. And then and so on. So if the power of the operator is 2, that will be yt minus 2. If it's 13, it will be yt minus 13. So we do the same very systematically on both sides. On the right-hand side, you are multiplying the coefficients by white noise, right? Once you do that, you leave only the y star t on the left-hand side and move everything to the right-hand side. Okay, so notice how I have now left the y star t. So this is starting to look more like a regression model, right? It's a regression model where the dependent variable is y star t, and the independent variables are variables that are also the same yt and some residuals left from previous fittings, right? From fitting of past observations, these residuals being white noise, right? So this looks very much like a model that has one dependent variable, and now how many independent variables? 1, 2, 3, 4, 5, 6, 7, 8, 9 independent variables. And those independent variables are all functions of the past behavior of the series. Now, notice something to keep in mind. When you have had differencing, there will be independent variables on the right-hand side that do not have a coefficient, a regression coefficient. Most of the other variables have regression coefficients, but the variables that are extracted from the polynomial that represented the trend from this one, for example, and then they are not going to have a coefficient. And that should be an indication to you that there has been differencing done to the time series, okay? And so what else can we do? Well, then we have our forecasting model or more done. This is the model that we have come up with. Obviously, for the forecasting model, we are going to put a hat on everything. And I just realized I forgot to put the hat in every single Y. So everything here is just being estimated, right? So most of these values will be already estimated. Why? Because they come from the fitted model, right? Our polynomial, we use the training data, and with the training data, then we are going to forecast. So what we are going to use from the past is going to be actually, hold on a second. No, actually, it's not going to be unless we run out of observations. So let's just not put the hat so quickly, okay? Let's just leave it like that. But notice we removed the WT because it's the forecasting model. Actually, we're going to plug in our actual values unless we have run out of actual values, unless we are forecasting a lot in the future. So let's forget about what I said about hats on the right-hand side for now, okay? So, all right, so this is our forecasting model, and we can use it to forecast. So this is what in the background R is doing. And so let's practice, okay? I just did a little bit with run. I extracted the last, let's see, 18 observations in the time series. So we have 156 observations. So we have N is 156 in the training set. So let's forecast. Let's do manual forecasting. Of course, we got it with ARIMA, but now we in the predict function. But now we want to do it manually. Excuse me. So what I'm going to do is show you how we use this equation, right? So we are going to, what are we going to do? Well, to forecast, we want to forecast why the last observation is, let me write everything for you here, okay? So notice what each observation is. So why a time 150, time means the time index, right? So this is actually December 1989 is the 156th observation. 1989 November is actually the 155th observation. So, so then what we're going to do is plug in the values of the time series, right? Where the Y stars 156 is, we are going to put 5.340. When the Y star 155 is, I'm going to plug in 5.175. Where the Y star 144, I'm going to put 5.322. Okay, so I know the last observation is the 156th observation, right? So in order to find that out, I had to figure out the length of the time series in the training set, right? So, okay, so we are going to plug in all those numbers. So this is the data on the training set, okay? This is actually the square root, okay? So this is the quartic rooms, not the square, the quartic rooms, okay? So we are doing the forecast, and the software is doing the forecast for the quartic rooms, because R doesn't understand that you did a quartic room root, okay? The ARIMA command will not, the ARIMA notation doesn't incorporate whatever pre-transformations you are doing. All right, so what do you do for the W's? What do you put for the W's? Well, the W's really are the residuals, right? At that particular time point. So the residual at time 156, at observation 156, the residual at December 1989, this comes from the model fitting. Okay, so the model that you fitted to the training data produced residuals. Remember that we analyzed the residuals of that model. So you have to pull out the residuals, right? And then you look at the, here is the command, you can get your residuals here. So I extracted for you the residuals, And so notice, pay attention to the R code to know what it is we are extracting. You extract the residuals, and then again, the residuals have a time index, right? And you can use there should be another one, yeah, here. So we have, for W145, we put the residual for January 1989, minus 0.026. So we bring this number for 145 here. So these numbers going here. Then the 144 is this number goes here. The residual for 156 is this number is going to go here, okay? And remember that the 143 here goes here, the Y144 goes here, the Y156 goes here. So when you substitute all these numbers in your expanded and forecasting model, you obtain the forecast 5.2427. This is a forecast for the quartic rooms, okay? So this is for the quartic, not for the actual rooms. So this is what R is producing. R is producing forecast for the pre-transformed variable. And that's what we obtain. So let's go back to what we obtained with R. Remember, I showed in the previous lesson, forecast ARIMA lectures part 2. We showed the result of the forecast, and the forecasted values were here, okay? So this is the actual data, right? And we forecast like our forecast for the pre-transformed data. So we need to do this last crucial step of converting the forecast to the original units. So we have to, if we did quartic root, we'll have to raise to the power 4 to obtain our actual forecast. Okay, so this is what we obtain, 755.5245, which corresponds to this forecast here. Now you may say, well, yours is not exactly the same as the one that R gave us. Well, it's pretty much the same. Why is it different? Well, let's go back and show you why it's different. Notice what I did here. I rounded. R is not rounding. Okay, R is working in the background. Why did I round? I rounded so that I could show you here in the screen all the numbers. Otherwise, I have like 7 or 8 decimals and it doesn't fit in the screen. If you don't round, you're going to get exactly the same answer that R got, okay? So I hope this lecture shows you that you can understand and see ARIMA modeling really like a regression model in which you're forecasting steps ahead, right? The future times using past times. But the process of obtaining the model requires all these steps that we have done, okay? You need to express first the model in polynomial form, multiply the polynomials in order to obtain the right model. Because everything in ARIMA is multiplicative. The MA seasonal and the MA regular is multiplicative. If you had had a seasonal AR, it would be multiplicative with the seasonal. With the regular AR, okay? And the trend is multiplicative with the model. So if you don't do this polynomial setup first, what's gonna happen is that you're going to end up with a wrong model, okay? So you only obtain this beautiful final expression if you do start with the polynomial form, okay? And this is the process that you need to understand. These models come from a very elaborate way of seeing and very holistic way of seeing the modeling of trend, seasonal, and short-term memory of the time series, which sometimes is very interesting, okay? So this lesson will explain the mathematics done by the software after a model is fitted to obtain the forecast, to obtain your model. And we saw that the math starts by representing the ARIMA model in polynomial form, translates everything we did to the data plus the fitted model in compact form, puts it all very compact, and then continues the math by expanding the polynomial, writing the result in a familiar way for us as a regression model. And with this familiar regression model, then we can forecast steps ahead by just plugging in values of the time series.